Dear colleagues and members of the International Conference on Digital Technology Driven Engineering 2025 community, my name is Mouangui, and I'm pleased to present our work entitled Adaptive Cross-Search Algorithm with Dynamic Neighborhood Structures for the Flowshop Scheduling Problem. This research has been conducted in collaboration with my supervisors, Professor Samira El-Moumen and Professor Mohammed Naimi. Our work is affiliated with the LIS laboratory at the Faculty of Sciences of Ain Shaq Hassan II University in Casablanca and LabSAD laboratory at the National School of Applied Sciences in Burshid. Today, I will briefly introduce the context of the flowshop scheduling problem, then present the main contributions of our adaptive cross-search algorithm, followed by experimental results and future works. I will structure my talk as follows. First, I will introduce the flowshop scheduling problem and its computational challenges. Then, I will explain the standard cross-search algorithm, its limitation, and how we enhanced it into an adaptive cross-search algorithm. Finally, I will present our experimental results, conclusions, and future work. The flowshop scheduling problem, first introduced by Johnson in 1954, involves processing n jobs on m machines in the same fixed order. The classical objective is to minimize the make span, which is the total completion time of all jobs. This problem is proven to be NP-hard for 3 or more machines, meaning exact optimization methods become impractical for real-world instances. That's why efficient meta-heuristics like the one we propose are essential for finding near-optimal solutions in a reasonable time. This diagram shows a simple example with 3 jobs and 3 machines where the make span is a 12-time unit. The cross-search algorithm is inspired by crows' intelligent food hiding behavior. Crows remember hiding spots and follow others to discover better locations. A simple yet effective metaphor for optimization. The key parameters include fly length, which controls exploration distance, and awareness probability, which introduces randomness. Each crow maintains a memory of its best solution. However, the standard cross-search algorithm has 3 major limitations. First, static parameters that don't adapt during search. Second, a fixed search strategy regardless of the problem. And the third, a tendency of premature convergence getting trapped in local optima. This motivates our work to transform the cross-search algorithm from a static to an adaptive algorithm. Here is the overall structure of our proposed adaptive cross-search algorithm. We start with niche-based initialization for only the first crow, then apply adaptive local search with a mix of insertion and swap moves. Parameters fly length and awareness probability are dynamically adjusted. If stagnation is detected, a perturbation mechanism is triggered. This continues until the maximum iterations are reached. Our first innovation is adaptive neighborhood selection. Insertion moves, shown here, promote global exploration by relocating a job. Swap moves, which exchange 2 jobs, enable local refinement. We use a strategic mix, 70% insertion for exploration and 30% swap for exploitation. This balance helps maintain diversity while refining good solutions. Second, we introduce dynamic parameter control. Awareness probability increases linearly over time to favor exploitation later in the search. Fly length decreases linearly to reduce exploration gradually. These adaptive rules enable a smooth transition from exploration to exploitation, responding to the search progress. Our third innovation tackles stagnation. We measure stagnation as the number of iterations without improvement. If this exceeds 25, a restart is triggered. The worst third of solutions are replaced using a hybrid strategy: 60% guided perturbation of the best solution and 40% random perturbation for exploration. This flowchart illustrates the restart process. When triggered, 60% of the time we perturb the best solution with local search, and 40% of the time we generate random permutations. The improved solutions are reinserted, allowing the search to escape local optima efficiently. To ensure efficiency, we implemented several optimizations. Just-in-time compilation using a NAM budget for critical function achieve 10 to 100 times speedup. Delta evaluation for fast neighborhood insertion and swap moves. Also, NAMPI arise for vectorized operation, and selective local search applied only to promising solutions. The cross-search algorithm uses continuous values for solution encoding. To apply cross-search algorithm to the permutation flowshop scheduling, which is a discrete problem, we adopt the smallest position value rule to convert continuous numbers into job sequences. The SPV rule sorts the position values in ascending order and assigns job indices accordingly. The table below provides a simple example illustrating this mapping. We evaluated our approach using tiered benchmarks ranging from 20 to 500 jobs. We used 20 crows and 115 iterations per run. The performance is measured using relative percentage deviation compared to basic cross-search algorithm. Each instance was run 20 times independently. Our results show consistent improvement. As seen in this table, adaptive cross-search algorithm outperforms basic cross-search algorithm across all instances, with an average RPD improvement of 8.89%. For example, for this instance, make Spain improved by over 13%. Notably, adaptive cross-search algorithm is also faster computationally for most instances size. This study demonstrates the effectiveness of hybridizing adaptive mechanism with the cross-search algorithm for permutation flowshop problems. The proposed adaptive cross-search algorithm enhances solution quality by combining adaptive parameter control, intelligent stagnation management, and strategic local search, achieving an optimal balance between exploration and exploitation. For future work, we plan to incorporate more neighborhood operators, implement automatic parameters tuning, test on large benchmarks, and extend the approach to multi-objective optimization. This research builds upon foundational work in optimization. Johnson's problem definition, complexity proof by Gary and Johnson, Askalzade's bio-inspired algorithm, local search theory, and tiered standard benchmarks. Finally, I would like to sincerely thank the conference organizers for providing this wonderful opportunity to present our work, as well as my supervisors, Professor Samira El-Moumen and Professor Mohammed Naimi for their constant support and encouragement. Thank you.